Recording in progress.
So we're going to start section 5.6, Math 7. So this one starts on page 206. We'll see how far we get, but I think it ends at the top of page 209. All right, so this one covers rational expressions. So when we talk about rational, what does that usually make you think of, right? A rational number is a fraction, right? So as long as b does not equal what? 0. Yeah, b cannot equal 0. We can't have 0 in the denominator. So these are always rational numbers. So when we talk about rational expressions, we're pretty much just talking about what we've been doing. We have two fractions, or rational numbers can also be whole numbers, negative numbers, but we can write them in fraction form. And a lot of what this involves is making sure that you've got your order of operation down. So we're going to learn how to simplify expressions involving decimals and fractions. And then we're going to simplify the square root of some rational numbers. So I'll show you all how to do that as well. All right, so first, a quick reminder is we've got our, I'm so glad they do it this way. I changed it before, but GEMDAS, y'all previously probably knew it as PEMDAS. What do you think that G stands for? Why is it not P? Because the P stood for what? Parentheses. But you really want to think of it in terms of grouping symbols. We'll get into that a little more. The E stands for exponents. And then, of course, the inverse of exponents are square roots. So this is included too. Or any sort of radical. M and D, these are both kind of the same level. So you work left to right. Multiplication, division. These trucks are busy today. So we work left to right. And the same thing with these last two, addition and subtraction. These also work left, right. We're down to just addition and subtraction. So the really important thing to remember about order of operation is if you have addition or subtraction inside of a grouping symbol, that means that you would do that addition subtraction first because of the parentheses or brackets, absolute value, square root, whatever that grouping symbol is. And so we can kind of go over some of those. I don't know if I can cover all of them, but I don't have them in front of me. I might miss a few, but grouping symbols. We have our usual suspects. We have the parentheses, it's sort of our base layer. And then if you have order of operation, if you have parentheses inside of another expression, it might have brackets. Call those like staple brackets or straight brackets. And then if you have even more, you might also see, which I'm really bad at drawing sometimes, curly brackets. So these set the order of operation. Oh, it's exploding. I'm gonna move that over just a little bit. So there's like regular order of operation grouping symbol. But we also have these guys here. What are those straight lines called? Are they familiar? Don't remember? This is absolute value. So no matter what the sign of the term is or the expression is inside the absolute value, when you solve it outside of absolute value, it's positive. However, before the numbers inside absolute value interact with anything else, you must solve them first. You must simplify them into whatever their positive value is. Another one is, and we put parentheses around it, but any kind of exponent. If there's an expression, let me put like an example. So if I had like, what's a good example? If I had 3 times or 3 plus 2, right, inside, even though it's addition, because that whole expression is being squared, I would have to make sure I solved 3 plus 2 before I apply it, before I squared it. And then on that same note, anything if you have 3 plus 2 inside of a square root, that also is a grouping symbol. There's maybe some more, but if we get to them, we'll come to it. But I just wanted to kind of review a little bit about like why we change it, because grouping symbols can be more than just parentheses. Oh, the fraction bar. That's another one. That's a big one. So if I have 3 plus 2 divided by 6, that fraction bar is also a grouping symbol. I need to solve that 3 plus 2 before I divide by 6. So sort of an understood parentheses there. Okay. All right, so let's look at our example from the textbook. So if we're working with order of operation, if I have 3/5 plus 2/3 times 1/2, what would I do first? The multiplication, right? Order of operation tells me that I have to solve the multiplication first. So I bring the 3/5 down because it's not interacting with anything yet. And then this is just 2/6. So now I can add my two fractions, but what do I have to find first? I need a common denominator, right? And I think the closest common denominator between are always, yeah, the closest common denominator to these two is 30. So 5 times 6 is 30, 3 times 6 is 18, 6 times 5 is 30, 2 times 5 is 10. And so we end up with 28/30. And then what do we always do? Wait, hold on. Oh, yes. We always reduce. So I can divide these by 2, and I get 14/15. Easy enough? Okay. Absolutely. I feel like this is, y'all should be fine with this. I feel like this is very easy, but I'll go ahead and do the example anyway. Example 2 gives us some practice using order operations with mixed numbers. I know, right? Let's take them out, put them back in. Okay, so we need to simplify 6 3/8 divided by 3 1/2 minus 1 4/5 plus 5 1/4. Oh, so much, right? So order of operation tells us that our first step is to solve inside parentheses first. First step. And so that takes care of this guy right here. So what do you want to do here? Do we need to convert them to improper fractions? to when because what are we doing inside the parentheses? We're subtracting. So we don't have to worry about turning them into improper fractions. Instead, what do we have to make sure of when we add or subtract fractions? We have to find the common denominator. So in this case, it's going to be 10. So I multiply times 5 over 5 up here and 2 over 2 down here. And so that's going to give me 5/10 over 8/10. All right. So can I do 5/10 minus 8/10? No. All right, so I'm going to borrow. Go back to here. So I'm going to borrow 1, so that's going to become a 2. What do you think I should add to 5/10? I mean, obviously I'm adding 1. 10 over 10, yes. Yes. Right, just match the denominator. And now we can do 15 minus 8. Put that here. All right, and that gives us 7/10. And then 2 minus 1 is 1. All right, so now we have solved inside the parentheses. I'm going to plug that in to my original problem and just rewrite it. I know it takes up, at least on my screen, it's taking up a lot of room, but make sure you give yourself plenty of room to figure out what's going on. All right, so I have 6 3/8 divided by 1 7/10 plus 5 1/4. So what do I do next? I'll give you time. Okay, so which part do I solve first? Okay, 1. Order of operation. So order of operation tells us we always do multiplication and division. There's no grouping symbols left. There's no exponents, but we do have a division. So let's go ahead and do our division. So as I rewrite this, I'm going to rewrite it as a mixed number. 8 times 6 is 48. 48 plus 3 makes 51. So 51 over 8. And, well, I'll keep the division. And then 10 times 1 is 10 plus 7 is 17 over 10. So step 2, solve division. All right, so 51 over 8 stays the same. What do I have to do? Change it to multiplication, and I multiply times the reciprocal. I bet 17 goes into 51. What's 17 times 3? Is that, I know, ends in 1. And if I carry my 2, 21, that becomes a 5. Yep. So we can reduce. So we know that 8 and 10, 2 goes into it. So that becomes a 4, and the 10 becomes a 5. Always with the trucks. And we know the 17 goes into 51. So the 17 becomes a 1. 51 becomes a 3. And so now this just becomes 3 times 5 over 4 times 1, which gives me 15 over 4. All right, turn it into a mixed number. So 4 goes into 15 3 times. 15 minus 12 is 3, so 3 3/4. All right, so I'm going to go back to my original problem. So I've gotten rid of that first part. So this is 3 3/4 plus 5 1/4. Hallelujah, we got the common denominator. So now our final step is we solve the addition. All right, common denominators mean that I can just, I'm actually going to turn this vertically. So that was what, 5 1/4? All right, so 3/4 plus 1/4. 4/4, which is 1. So I'm actually just going to go ahead and add that 1 here. So carry. So 5, 6, 7, 8, 9. So 9 is my final answer. After all that. They do give you a lot of practice. I'm just going to give you a few. If you can show me that you can do it, we're not going to worry about it. I would rather spend the time working on the next part, which is simplifying the square roots of fractions. Now, so when you are finding, I'm trying to figure out if this is going to make it more confusing or less. Let's just talk. Let me try it and we'll see if it helps. Yeah, for now. Simplifying square roots. We have learned this, but just to kind of put it in a sort of a different perspective. So if you are finding the square root of A, then you are looking for the number B, such that B squared equals A. So let me give you an example. So let's say A is 4 and you are looking for B. So what number, I'm going to use the variable B, what number squared equals 4? So you are, when you are squaring, so if you're squaring the square root of A, or excuse me, you're finding the square root of A, you're looking for B, which is a different number, but it is the number that if you squared that number, it would give you A. So what number times itself equals 4? 2. So B is 2. Right? So that's why I'm using A and B, because they're two different numbers. Like you would never find the square root of 4 and get 4. Right? And you can check it by plugging in that value and saying that 2 squared equals 4. That's a true statement. Therefore, the number you're looking for is the 2. So let's look at how we do that with fractions. All right. So if I have, actually, I'm going to do the second example. We'll just write it. Okay, so if let's say we have the square root of 25 over 144. So the nice thing about finding the square root, and this works with exponents as well, is you can sort of divide that grouping symbol, in this case, the square root, to both the numerator and the denominator. So this rewrites as the square root of 25 over the square root of 144. So what we need to find out is what number squared equals 25 and what number squared equals 144. So can you think of any numbers that what times itself equals 25? 5 times 5. So x equals 5 because 5 times 5 is 25. So that means the square root of 25 is what? 5. What about 144? Okay, So 12 squared equals 144. So that means that our denominator, that was like really messy, just underline it. So that means that x equals, or the square root of 144 equals, what is my denominator? 12. So we are done. Now, if we want to check if we're correct, then we do the inverse of square root. So what's the opposite of, what's the inverse of square root? So think of inverses like, what's the inverse of addition? Subtraction. What's the inverse of multiplication? And what's the inverse of square root? This guy right here. Squared. Yes. So we can always check it by having 5. So this is our check. You square the fraction, 5 over 12 squared, because exponents work exactly the same as square root. This is 5 squared. Think of it as the distributive property. You're distributing the squared and the square root to the numerator and the denominator. So this is 5 squared over 12 squared. And we just determined that 5 squared is 25 and 12 squared is 144. And that gives us the numbers that were inside of our square root, so we know that we're correct. Finding the exact square root of a fraction is possible when both the numerator and denominator are perfect squares, or when the quotient simplifies to a perfect square. But we don't always have that as an option. The square root of any number that's not a perfect square is an irrational number. So let me show you what we do in this case. Come on, keep moving. Show you what I mean. So like, what are my perfect squares? So we're looking at 1 times 1, 2 times 2, 3 squared, 4 squared, 16, 5 squared. Right, and then we keep going, right? These, so 1, 4, 9, 16, 25, 36, 49, 64, 81. Those are 100. Those are all perfect squares. So if they're those numbers, it's good to kind of memorize those. And we see them a lot in our practice, so you'll sort of start to recognize them. But sometimes you don't have a perfect square. And we cannot leave an irrational number in our denominator. So I'm going to show you what we do with these. So for example, for identifying rational expressions, we'll probably stop at this one and finish tomorrow. All right. Oh, they just have us. Well, we'll solve them. Identify each square root as rational or irrational. So what we do with these, so if we have the square root of 180 over 5, obviously 5 is a prime number. So it is like as much of an opposite as you can get from a perfect square, right? So we do not have a perfect square. So what you want to do if you obviously don't have a perfect square in either the denominator or the numerator is simplify the fraction first. So before, I knew, and y'all will start to recognize it, that we have perfect squares. So it made more sense for me to just go ahead and square the numerator and denominator separately, so I could turn them into 5 and 12 in our previous example. In this case, I know that 5 is not a perfect square of any kind. So instead, I want to go ahead and simplify 5 into 180. Only do this if you know you're going to get a whole number. Like in this case, it ends in 0, so I know 5 is going to go into it. If it was 32 over 4, Like we know 4 goes into 32 8 times. So you can simplify that first if it's a whole number. So in this case, 5 goes into 18 3 times. That gives us 15, bring down our 0. 5 goes into 36 times. Trucks are so loud. And then you can check if rational or irrational. So in this case, we have the square root of 36. Now, is 36 a perfect square? So what times itself gives you 36? Right? We know that 6 squared is 36. 6 times 6 is 36. So the square root of 36 is what number? What is the square root of? It's 6. And is 6 rational? Absolutely. So our answer is yes. Or I'm sorry, I should not yes. I should put rational. That's the answer we were looking for. All right, let's look at another example. Yeah, let's do B. So the square root of 219 over 3. All right, so how do we know if 3 goes into 219? Without doing the division. Like, do we know that 3 goes into 219? We can find out because we add the digits. So 2 plus 1 is 3. 3 plus 9 is 12. So 3 definitely goes into 12. Therefore, it goes into 219. So let me go ahead and do the math here. So 3 into 219. 3 goes into 21. 7 times, no remainder. So bring down my 9, and 3 goes into 9 3 times. So this gets me the answer, square root of 73. So is 73 a perfect square? So we know that, let's see, 8 times 8 is 64. 9 times 9, and this is how we check. So 64 is 8 squared, right? It would be 8. And 9 is what? 81. And 73 falls between them. So 73 is not a perfect square, so that means it is what? Rational or irrational? Irrational. My internet's kind of going. There we go. Irrational. So if the number inside the square root is not a perfect square, it's irrational. Okay. Let's see. We don't want to do. I'm not going to fool with that. Let's do. So page 209, number 3 through 5. Let's see what I skipped here. Okay, none of those crazy ones. 26 8. Okay, let's just do 8 through 26 even. 3, 4, and 5 should be pretty simple. You're working with the square roots and trying to just either simplify them to their fraction if they're rational, or tell me that they're irrational if you can't do anything with them. And then, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's kind of those multi-step with fractions. But I think 10 is plenty. That's plenty to get some practice using order of operation and knowing whether you know how to do it or not. All right, that'll be it.